can still watch. Um, so, it, I'd like to hear from some others, but if people do like the online video thing, or sorry, the online face to face where we have the discussions and I record them, I'm totally good with that. Any other people want to make comments?
For the videos because we can like rewatch them for reference and study, but this isn't bad. Whichever's easier for you, honestly.
Well, the big thing I want to do, I mean, pure easiness, just sitting and talking to everybody here, and I can pull up my whiteboard and I'll try to get a fancier setup for that. Um, now I just grabbed a whiteboard I had available and figured we could walk through it and I'd see how that goes. But I can mount the board on a wall somewhere and make that work for future ones if we prefer this type of a setting. But I do want to get whatever's going to be most useful for all of you because it's not helpful to spend time if people are not going to learn from it. So on the chat side, I see comments like I like face to face, especially if the meeting can be recorded for later viewing. And the meeting can. So that's what I'm doing right now. What I've discovered with WebEx is the recording is like really weird. It'll pop in like somewhere between 4 to 8 hours. So if you go to WebEx and you see the calendar, let me see if I can. When you go to that kind of calendar view, there's a menu bar just above where the calendar was that says event calendar, appointment booking, event recording. And if you click on event recording, it will show you every WebEx that has happened in the class. And it will give you an option to be able to, um, it'll say the name of it and when it happened. And it'll say either check for recordings or tell you there is a recording. Um, and if you click check for recording and it's within like 8 hours of the class, it'll tell you, nope, I didn't find it. There's none there. Because it processes in the background. And with pretty much everybody hammering WebEx, the video processing is stupidly slow. So I've noticed it usually shows up really late that night or early the next morning. And then I search for it and it's all of a sudden there. Um, so that's just a note if we do decide we like the face to face with recorded. Any other thoughts or comments? Um, so for the people who like the recorded videos, um, is that mainly for the ability to repeat? Would the recorded video from a face to face also be useful? Yes. Okay, awesome. People are using the chats also. So I'm getting yeses. Um, so I'm gonna then not worry too much about the non face to face stuff. I might stick a couple in just as kind of where I think it will help on the book. We will try to get onto the book schedule as fast as we can, just so we get through as much material as possible. There are a few places where I think it might be helpful to do some things. So I might, for instance, do a recording for the when we do Verilog and just uh, do a screencast of my screen. So you could just see me typing those and then do it in advance of a class and then we can talk about it. And I'll try to keep those. If it's under 10 minutes, is that easier for everybody to focus?
Yeah.
Is it good to do a video of the actual Verilog code, or would it be better if I just posted Verilog code and then we talked about it in the face-to-face. Just posted video and talked about. So it seems that there's kind of a mixture. So maybe what I'll do is I'll take the write up the codes when we're going to deal with them. I'll post them in advance, and I'll give a brief, overview of what's happening inside, and then we can talk about it face to face. So I'll try to make sure I get those up with at least one day before the lecture discussion, so that we can maximize our time. So do try to keep up with the book. From what I got feedback, most everybody should either have the book, or I posted a link where you're supposed to be able to get the book for free, at least online access to it through the end of the semester. Was anybody not able to get access to the book either of those two ways? All right, seeing nothing, I'm going to presume that everything's okay. If you were not able to get a good access to the book, please do let me know, so I can work with the book publishers to make sure you get something. All right. So I'm gonna try to. We'll see if I can focus this a little bit better. So I'm trying to balance my my computer. My house isn't really set up as a schoolroom. Okay, so what we want to talk about in this second half, and I'm going to hit some of this a little bit lightly because there are videos that cover the details, but I want to get at least a big picture since not everybody has been able to see the videos yet. So we're going to be talking about what's called sequential, synchronous, circuits, or well, I'm just going to use circuits. Everybody read? It's hard for me to tell how big this is because they stick me in this little tiny window. Yes, awesome. Okay, so there's two parts of this. One is sequential. The sequential is going to be what's going to cover our idea of memory. And why we use sequential is sequence matters. No longer like with combinational, is it just I've got some inputs, and from the inputs, I can uniquely determine what the outputs is. I need to know all the previous inputs, and I need to know the order they happened in. So the sequence of the inputs matters because that will allow me to determine the internal memory or the internal state of the system. Now, synchronous is a subset of sequential. Sometimes people say synchronous sequential, but I'm doing it specifically this way because this is the big category. This means it's got memory. The sequence of the inputs matter. This is going to tell you SYN means with, sin with chronos, right? Which means clock. So with a clock. So that means we're going to want to be able to clock this. And if you remember on the first part of the semester, we spoke about using a clock inside FPGAs to remove errors of type 1. So we could do error of type 1 removal by doing a nicer design like you would find with Cardinal maps and things of that sort. Or to make your life easier, you could use a clock. So you kind of hold the value in between the areas. And the idea with a clock is we'll just have this repeating pattern, right? low, high, low, high, and just nice square wave on it. So 0 to 1. And the clock will just keep repeating. And we're going to want to know exactly. So, for instance, like on a rising edge, and we'll only look at the circuit at the rising edge, and everything else will be ignored. That way, if there's glitches that happen between those rising edges, we don't have to worry about them. It only matters what's happening right at that instant. So hopefully that makes some sense. So that's kind of the goal. So this means we're going to use this clock. There are ones, and initially we're going to have to deal without a clock and then build up the circuits that have a clock. So we have two types of memory elements, two types of sequential. One is called latches, and the other are called flip-flops. The latches are the simpler circuits. They do not have a clock, so these are asynchronous. Flip-flops are going to use a clock, um, and they'll be edge triggered. So these ones will have an edge trigger to them, so they are synchronous. There will be a subtype of latches that have enables that will still be asynchronous, but they'll kind of have a safety feature. You can disable them and they'll just hold their state. But that's kind of like a special little subcategory. Now, these are going to generate some special constructs inside of your Verilog. So to generate both of these, when you do an always, so we will make these every single time with an always. Particularly for the flip-flops, this is what you're going to spend your time on. So I'm going to mention flip-flop first, because that's our big concern here. We're going to say at, and for instance, with our clock, if we're measuring on the positive edge when it goes from low to high on the clock cycle, that transition, we'll say always at pos edge, POS EDGE of whatever you're dealing with, which in our case will be like clock. You can also do neg edge, NEG, EDGE, right, if you want to get the falling edge. And then inside you can put your code as you normally would for any of the always threads. And this is going to be characteristic of what you will do for a flip-flop. We'll get into more specifics of how to make flip-flops, but the second your Verilog compiler sees this at pos edge clock, it's going to go, oh, you're building something that has synchronous sequential memory. And so synchronous sequential is going to go to a flip-flop. So it's going to assume there is going to be those states in there. And, when we go to latches, latches do not use the edges. So they're going to look just like combinational circuits. When you do them, you're going to have the always at star. And that will create some kind of fun issues for them. But we won't deal very heavily with latches past our initial first couple lectures, or first couple videos and my kind of overview here. Because that is basically, it's kind of a dangerous thing to design with. So you have to know in advance what you're going to be doing, and so that's kind of an advanced. Um, just a quick check to everybody. Is everybody following? Are we good?
Yeah.
Okay. It's just different because normally when I'm lecturing, I can see your faces and I go, "Oh, okay, everybody's solid." So, all right, that's kind of the idea with the flip flops. Like I said, we'll deal with code more as it goes on, but we're going to really want to deal with these flip flops. So you're going to want to get used to this pos and neg edge as the event for your always block. All right. Let's talk about how we can build these. So if anybody has watched the videos so far, or at least seen the beginning part of the pencast, how do we build a latch? You're welcome to unmute and speak. Makes it more fun anyway. No volunteers? A feedback loop. Okay, I see some in the text. Yes, feedback loop is exactly what we're going to do. I'm going to draw it different than I do on the videos because this is not the way it's normally drawn, but it'll make the feedback loop a little more obvious. We're going to use NOR gates and NAND gates to build them because we build everything with NOR gates and NAND gates. So imagine here for one sec, I'm going to take my NOR gates and just feed them back around like that. So I've got it fed back in, and this right here then becomes my output. So I've got two input lines and one output. Well, when we take these, if I were to take this and kind of pull it alongside and I flip this, I can leave the first one up where it was, and I could drag this so it comes back around and place this one down here. And then it comes out and feeds back into the other one. And then we just leave our two inputs. That's kind of how we generally set them up. And I'm going to call this top output Q. And then we have two inputs here. And consider for a sec, if I were to place a 1 right here. Right? So if I had a 1 in this spot, this 1 coming in on an OR, ignore the inversion for a sec. A 1 on an OR, you don't need to know what the other value is. So the 1s are going to be the things that are going to allow you to force through regardless of what's in that feedback loop. Otherwise, you'd need to know the feedback loop. So a 1 will force this OR to give me a 1 on its output, and then the inversion would give me a 0. That 0 is going to come around, and then without knowing whatever's over here, I don't know what's happening. So generally we say we want things to be zeros when it's the NOR gates. So I'm just going to leave that as a 0 here for the moment. And we'll consider kind of our truth table set up, our inputs. We've got our kind of our top input, our bottom input. Top input I made a 1, and the bottom input I made a 0. And my Q
Is that right?
is a 0. Is that a question or just? I think I'm just getting feedback. Okay. So if we've got these right, so now I've got zeros on both. An OR 2 zeros gives me a 0. Inversion gives me a 1. Now I've got 2 1s over here, which still gives me the 0. So it becomes nice and stable. So the bottom here, what's coming out, we call Q prime because it is always the opposite of Q. Now, that always is kind of asterisked. And there are ways I can force them to be different. But if it ever gets to the point where they become the same, then I'm not going to be happy about that situation. That's a very dangerous situation. So we're going to work hard to make sure that they always stay opposite each other. Therefore, we get Q and Q prime. So the asterisk is in normal operation, and we'll build our circuits to avoid it. Okay. Um, so does this make sense to people? Cool. I'm getting yeses. Okay. So we're going to now go. Remember, I said kind of 0 is our standard. So this one turned Q to 0. So we call that reset. We sometimes call it clear. And that's why the top one will eventually be called R. If we put them both to 0, now I take this and I switch this. So that becomes a 0. And the question is, does it affect the outputs? Well, I've got this zeros coming around to here. So this input is a 0. I've got this 1 coming over here. Well, 0 nor 0 still gives me a 1. And 0 nor 1 still gives me a 0. So it holds the value. So therefore, the value doesn't change. But it only didn't change because that's what was already there. That's why we call this state whole. And we'll show in a sec here, we'll go to 0, 1. We said the top one here counts as R for reset. So now we're going to go to 0, 1. So the bottom one has to go to a 1. Okay. Now I've got the 1 on. So the second that 1 is here, that's going to force this to go to 0. Now at the same time, I haven't done to the top one. So for the first initial little tiny bit of time, the old one is still there. It technically takes some time to go down the wire. The old one is still there, which means this 0 is held for a little bit. So the first little fraction of a second, it goes to this 0, 0. But then shortly thereafter, the 0 comes down. And then I've got 0 nor 0, which goes to 1. And then for a little while down, it takes for this one to propagate. But since there's already a 1 there, it doesn't matter. So it takes, technically speaking, for that 1, that's when the internal has completely settled. Once it's settled, you can remove that. Until this 1 comes down here, it won't hold the value. So this is actually kind of a big issue, and I didn't talk about in the videos, but it does take a little bit of time for these values to percolate through and get to this setup condition. So you have to hold the input for a little while after you initially assert it, so that it takes time for the whole thing to percolate through, get the value stabled, and then once you have done that, you can now go back to 0. This set it as 1, 0. We call that set. When I go to 0, 0, this is 0 nor 0, it's still 1. 1 nor 0 is still 0. Once this 1 gets here, it will be able to hold this value. But until that happens, it won't. So this, again, did exactly what it was supposed to. It did a hold. So that time period that I had to maintain this particular value at initially 1 before I could set it to 0, we call that the hold time. We'll talk about a little bit later that sometimes you have to have the value there a little bit in advance and to hold it afterwards. And the initial time is called setup. So you have setup and you have which is how long you have to assert it before it kind of makes it through here and starts that hold time. And then there's the hold time, which is how long does it take to get through everything and stabilize it. Do the ideas of setup and hold make some sense? Okay, more yeses. Yes, yes, yep. Okay, cool. So now we've got kind of these states here. There's one dangerous state to us, right? And you can kind of imagine. So now we know that this is a reset and this is a set. Imagine I hit both reset and set at the same time. So if I hit both reset and set at the same exact time, this one nor whatever, right, is going to give me a zero. And one nor whatever is going to give me a zero. And I just hold those for a little bit, and those zeros come around, and but it still stays 0, 0. They're not opposite each other. Remember, I said this was going to be kind of dangerous. But right now, it's only potentially dangerous, right? It's kind of like I'm holding down the buttons and I've got it set up, right? It's like pulling the pin from a grenade or something, right? It's not at the moment about to explode. It's when I let the spoon go. Um, so this is just kind of primed up. And you can tell I'm still get spam calls here. Um, so once you let go here, when I go to the hold case, now if I were to go to either set or reset will fix the problem. But if I were to just go to hold, right, well, what's it going to do? Is it going to hold this? Well, unfortunately, when I've got all zeros in the system, right? Remember this zero's coming around, that zero's coming around. Zero nor zero is one. And zero nor zero is one. So these both change to one, which means they're going to come around after a little bit of time and they'll change the inputs to one. It's whatever the wire propagation time is. And then I'll have one nor zero, and that'll give me a zero. And same thing over here, which will then propagate down and I'll come back to the first case again. So basically, the second I go to hold, these are going to start flipping 0, 1, 0, 1, 0, 1, right? And it will flip as fast as that gate can propagate. So it's literally going to flip in nanoseconds or maybe even picoseconds. So just ridiculously fast. But since the wires aren't exactly the same length and none of these two are exactly the same, it's going to take a little bit different time from here to this value than it will from this value all the way through to here. It'll be slightly different, which will create a beat frequency from physics, which as they start getting out of sequence, the first one that ends up giving me a 0, 1 pattern, right? So whether it's 1, 0 or 1, 0, that one will hold. But I don't know which one am I going to get. And I don't know how many oscillations. If they're really well tuned, it'll take a long time before the beats separate in phase enough to make that difference. So the second I go here, I don't know what it'll end up at. I know it's either going to be 0, 1 or 1, 0, but who knows? So we just make this illegal. We just say you're not allowed to do it. Now, obviously, physically, you're capable of doing it. That's why we call it illegal rather than impossible. So, by rules, you are not allowed to use that state. If your system ever generates that state, what you'll get, this rapid flipping, and then at some point it settles on a value you don't know, is an example of metastability. Right. So we do not like metastability. This is one of our big threats. There's a couple ways we can get metastable circuits. This is one of them. We don't like this. So we try to avoid this very hard because we like to have things that have known performance with known solutions. Okay. Does the idea of how to build a latch and what it is make sense though? Okay, more yeses. So basically, as long as we leave this off, we're good with this, this, and this as our three basic commands. Okay. We can do the same exact thing with a NAND. The difference with a NAND is instead of having S and R, when you do a NAND, we're going to call them S prime and R prime because ones will be the values that are going to actually be the null state. So the 1, 1 or two NAND gates hooked in the same configuration will be hold. And a reset will be a 0, 1. And a set will be a 1, 0 because 1 is the don't do anything. Zeros in an AND gate produce a change. So, you know, that the big one for the other one is it basically just flips these values. So we just call them the primed versions, R prime and S prime. But otherwise, it's basically the same. It flips which one's which too. But the bigger issue is that you get that kind of flipped gate functionality. But the same idea happens. One feedback loop, one bit of memory. And if you notice, all I have, since Q prime is dependent on Q for all the legal versions, I technically have one bit. But I also don't know when it's going to happen. I mean, literally, whenever it will react immediately. Does that make sense? Doop, doop, yay. Okay. Now, so this was the NOR version. You can watch the NAND version online if you are interested. Um, the next major step up is that kind of second one in the sequence, which is the idea of an enable. We usually do these with NAND gates because we just tend to like NAND gates. They do make up the majority of our circuits, so we have more development time with them too. Maybe I should actually really quickly kind of do this one. So I've commented that ones are kind of our normative value. So if I go 1, 0 here, remember a 0 going into the AND gate is going to give you a 0 inverted gives you a 1. When I have a 0 coming into a NAND, I get a 1. The only way to get a 0 out of a NAND is to have all the inputs 1. Now I do have on this next one, I've got this 1 kind of comes down, and I've got 1, 1 going into this NAND, which means I'll get a 0. Again, we keep the top one as Q, which means this is R prime. If I put a 1 here, then you'll notice I have 1 NAND with a 0. So I still keep my 1. And then the 1 and NAND 1 still gives me the 0. So 1, 1 still holds it. And if you make this a 0, the 0 on this NAND will make this a 1, which will eventually work its way down here and turn that into a 0. So this one is kind of, since this is Q, and that gives me a 1 as an output, this one's S, but we'd normally like to call if it was a 1, we do it, so we call it S prime. So remember, it's a 0, a low to set it. So that's the real quick intro to the NAND flip-flop. But the neat thing about this is I can come in and I can add in a second gate. I'm going to do a gate for each of these. Again, NAND gates. And now I'm going to call this one S and call this one R. I'll explain in a sec. And this one I'm going to do EN. Now, if EN is equal to 0, imagine I put a 0 on this line here. This 0 will go into this NAND gate, and 0 goes into an AND gate, you get a 1. I will get this to be equal to a 1. That also goes into this, so this R prime is also equal to a 1. Remember, if both of these are 1, it does a hold. So I've got the enable, and then SR. If enable is 0, it doesn't matter because I didn't even look what those were. I know the function I get is hold. Now, if enable turns to a 1 into an AND gate, I need to know what the other value is. So now if I set both of these equal to 0, and I have 0 into an AND, which gives me a 1, 0 into an AND gives me a 1. So once this goes to a 1, if they're both zeros, it'll still do hold, right? Because both ones at this level works. So the kind of the neat way I think of this enable, the way it's hooked up here, an enable 1 hooked into these gates basically turns these into just inverters. Because 1 NAND R is just R prime. That's why we call this R, and that's why we call this S from the prime. It's because if you prime a prime, you get back to the original variable. So with that observation, I can just go 1 and go, well, if I do 1 on the R, I should reset. Leave that 0 there, means I still have a 1 here. 1 here means I have a 0 here. And we've already done that analysis here. The 0 NAND that puts a 1 here, which percolates around, and the 1 NAND 1 makes that a 0. So it does indeed do a reset. Hopefully it makes sense what's going on here, which means you should be able to note or just check on your own. If you were to flip them, it's symmetric, so you can realize it'll flip the values through here. So it will actually flip and do a set. And if you do all ones, then you get both zeros in here, which means you go to that danger state. You get to that 1, 1, and that is our illegal state. So the enable hasn't removed the enable or the illegal state, but it has allowed me to do a hold, and I can basically prevent these inputs from doing anything. And this is that first step towards our kind of clocking. So if you think about from a clock signal, I've basically made it ignore every time the clock is low with that enable, if I put the clock into the enable. And that's actually the really important part of this. I've basically removed half of my times. And sometimes that's all you need. But usually you need both sides. So, but this is kind of our first crucial step. And this is why, while you won't be specifically building these ones all the time, I do think it's important to understand why things work. Okay, do we feel good with the enable? Okay, more yees. Awesome. One last thing we're going to do on this is we really don't like this illegal, so I'm going to get rid of the illegal. Now, if you notice, I've got 2 holds. I don't need both of them. I'd like to get rid of this hold and this illegal. Both of those happen when S equals R. So I'm going to make it impossible for S to equal R. I'm going to do that by removing R and making R connected by a NOT gate. So now when you put your value for S in, R will get not S, which means they can only ever be in one of these two configurations. So the second I do that, that means whatever is the value here, that since that's set, that value will go through. So if I put a 1 here, I'll do a 1. If I put a 0 here, that means reset is 1. So I put a 0 up here. You can kind of see that value will carry through. Just because the way we've already analyzed it, so we don't have to redo the circuit analysis. We can just now draw our conclusions. Whatever value goes here ends up here. That means this is kind of now functioning like this is my data, and that's the stored value of the data. So I can send data in. So we call this a D latch or a D latch with enable. And that's the whole big idea here now is I can deal with just taking a value and telling it store it for me. And this is now really getting close to what you consider regular memory. So once I have a D latch, we kind of turn this into its own little special kind of box. We're going to call this our lovely component. And we're going to have a D and an enable. And we usually only show the Q coming out. We know that we can get Q prime if we want, but often all you need is D. So this whole circuit with this functionality, moving that extra hold, we still have hold, you just turn enable off. But now it is not possible to do anything illegal. We've made the illegal impossible, best of all cases. So we don't have to worry about it. Now, as a little side note, very often that means we actually put, truthfully, a little buffer here for timing purposes, because we don't want these to be off time and end up getting in a legal state temporarily. Okay. But anyway, that's kind of more fine detail. All right. Do we feel comfortable with the D latch? And Jake gives me permission. I got my next yee. So thank you, Jake. I hope that for everybody else, if it ever oh awesome, I got a yee and a yes too. So thank you all. I like to just every now and then do the ask because again, it's just all I'm staring at is letters on the screen. So I want to make sure all of you are following me. Okay. So we're going to take this and we now want to create an edge trigger flip-flop. There's two different types, one of which is kind of harder to understand. I'm going to cover the simpler one because I want to get the basic idea down for all of you. And the videos I go in more than enough detail to show you how the more complicated circuit works. So I'm going to do what's called the master slave flip-flop here because it's easier to explain. We've got our D and our enable. I'm going to label this for master, and it's got Q. And I've got a D and an enable and a Q for S for the slave flip-flop. And we call this one the slave because it is slave to the output of this one. Right? Means it doesn't get to choose what it wants. There's no other options. It can only take this one. So since it is hooked hard to this and has no choice, that's why it gets its name. So the enable is what we're going to do. This enable, I had said if we hooked it to the clock, basically we can ignore problems when the clock is equal to 0. So we're going to try to make it so that we can ignore problems when the clock is 1 on this. But to do that, if we invert, when the clock is 1, this one will be 0. Now, if you think at first, kind of blush at that then, right? This one only lets something through if it's a 1, And this one only lets it through if it's a 0. It sounds like I don't let anything through. And at one level, that's almost kind of true, but it's not completely true. There is this little tiny window at the end from what was happening just before the clock to what happens just after the clock that will sneak through, and it'll get held. And that's actually what really matters. So we've got our different positions. I'm going to call this our data D that comes in. And then this is our intermediate value, and this is our output Q. So if I go, let me draw, yeah, it's easier for me to draw up here. I got a clock, and it can be a 0, 1, and I've got my data, I got my intermediate, and I got a Q. So I'm going to do this. These will be our standard kind of drawing. So my clock is going to look like that. So my data D coming in, whatever, say that's my D. It's got all kinds of crazy things happen. Now, whenever clock is 0, it's not going to read anything. So during this whole time period, whatever I was initially, let's say I initially was 1, lack of anything better. The whole time while clock is 0, this is not enabled. So it's not reading what's happening to D. It's just holding the last value it saw, which I said I was going to set at 1. The second it goes high, clock goes to 1, that enable is on, and now D can go out to Q. So at this instant, and up until that instant when it goes to 0, I can exactly copy my waveform. The second it goes to 0, this is turned off and it holds the last thing it saw. We'll continue to hold it up until we hit a 1 on the clock again, which enables it. And then it will start following again. Oops. And then it will hold the last value it saw until it gets enabled, and then off it goes. So that's what's happening right here at this I value. And you'll notice we're able to remove a lot of weird transient behaviors from my system. I haven't removed everything, but I've removed a lot of it. So now I is my input to the next one. And whenever clock is 0, this one's input is 1. So the next stage is going to copy whenever it is 0. So Q, for this system, it looks at what I is and says, I was high. Oh, bad. Did that wrong. Sorry. I've forgotten that was high. Ooh, that should go. It was high. There's my 0, 1. Goes to 0. And then it follows. I just drew everything too high up. And it still holds at that point. And then it starts switching. And then it holds. Switches. So I unfortunately drew it skewed. So I guess it wasn't technically wrong. It was just shifted. Okay. So my I is a 1. And this is during the time clock equals 0 is when my system down here can copy it over. So this whole time it's following, but the input never changes because this one was held solid during this time. The whole time this one's reading. So it can only ever read one value. And when it turns off and this one's varying, this one can no longer read because when clock is 1, the system connecting I to Q is not enabled. So it just holds its value. And then it looks and sees, oh, 1, and it only stays a 1 through the whole thing. When it goes to the high position, this one gets a low, so it, again, holds its last value. And when this one now, all of a sudden it goes low here, this one will turn high and it'll follow. It sees a 0, so it goes awesome. It follows that. And then following it that whole time, while this one is stuck fixed, when this one goes high, allowing that one to change, this one now gets a 0 and it's not allowed to change, so it has to hold its value. So for all those crazy squiggles going through 2 latches in inverse order, I've cut it down and removed everything except that key transition. And this is what's so powerful about it. I can reject all this kind of weird intermediate junk. Now, this can also be very dangerous because you don't want to, if this isn't junk, you don't want to reject it. But if this is temporary values and things, so you remember your circuits take a while to settle. Right? So if this is all just settling values, then you do want to reject them. But you'll notice we're able to reject them and we just get the values that are read at that one very precise time. Right? And what makes it through is this first one copies the value when it goes, right? Last value when it's high comes from here to here. And then whatever was copied there at this time, that value gets right, propagated down and then copied over. Those are kind of my shifts, and it will hold constant at that point forward because it's getting copied this whole time through. Just like this one was shifting, but it only gets copied down once. So this edge is the one that makes that difference. Okay. So anyway, you'll see that same thing, right? That because it's copying this whole time. So this time period is the only time that makes it through and gets help. So again, here, this time it makes it through and it gets help. You can see it's always on that falling edge. We call that a neg edge. So that's negative edge because if you calculate the slope, it goes from a 1 to a 0. It's falling, so it's a negative 1. All right. We feel good with the idea of an edge triggered flip flop. Yepper. Cool. Lots of different ways to tell me yes. Okay, cool. A yes. I see yours. Awesome. This will be our fun thing. How many different ways in chat use? Okay. So again, this is kind of our nice thing. So this is going to allow us to get very precisely timed things. Now, as I mentioned in when we're doing the area, there's kind of a period before that edge that it's got to be set up because this allows time for everything, all the values to be there and all the inputs to be properly excited. There's like a little window, right? The time before is the setup time, and there's a time after it has to hold, and that's called the hold time. So right around that neg edge, there's that little window, and everything has to be stable in that window. If it's not stable, then you have no idea what you're going to get. So if clock and D change at the same time right on that edge, we've got a problem. Or if D changes within a small period before or after. Now, the exact amount of that time is going to vary by the actual design. So, oh, I like the backward yes from Jake. Um, so the exact time of that will vary by design. So you'll be able to look it up on the spec sheets. So this is why spec sheets matter. So if you ever are working with a particular part, or even, that part could be an entire FPGA, when you're looking at their memories, you're going to want to pull up their spec sheet and find out what their timing constraints are. So one of the big things when you were doing your designs and you would run them inside of Xilinx is, since Xilinx produced Vivado, right, the software, all of Xilinx's timings for those chips are already known. The spec sheet's basically programmed into the system. So when you told it you're using whatever type of chip you're using, it already has the spec sheet and it will do those timing calculations for you. So it'll check to see, does the signal get there before it needs to? And does it stay stable long enough that I'm not going to have a problem latching it? So part of why it takes so long is it does that calculation check for every single wire in the entire system. So from one memory unit to the next, it literally checks everything to make sure that they're all timed rightly. If you ever get a timing error or a clocking error, it's telling you it wasn't able to meet those requirements, which means you can now get glitches. Your design can behave wrong. So if you see timing errors, it doesn't mean your design will behave wrong every time. It means you are now subject to glitches, which means it's almost kind of random. It's the scarier situation, right? It'll behave nicely for a while, and then all of a sudden it'll do something wrong, and they'll seem to behave right for a while. So that's when we start hunting into the error logs to try to find out, what was the timing issue and fix that timing issue. So, all right. Do we feel good with everything we need on flip-flops? Because if so, we're going to talk about a few other types of flip-flops, and then we'll start talking about how we analyze things. So, see, okay, we're getting into Spanish. A yes. MHM. Okay, I need help with that one. No, okay, I see French. A thumbs up. Totally cool. Okay. So now we're going to take this device and we're now going to call this whole thing a D flip-flop. And this is going to be our friend through pretty much the rest of the course. Our clock is done kind of like a duck mouth right at the beginning here. It's like a little sideways V or a triangle. That means clock. We don't write clock. That's what it is. So this means there's a D input on this wire. This little triangular bit here means that's my clock input. And if I draw, so as I've written it here, this one was a neg edge. So if I want to be proper, I put the little circle right out there. So if there's a circle in front, it means negative edge. If there's no circle in front, it means positive edge. So you can just look at that clock area and you can tell, and you just see this, oh, no circle, then you know it's a positive edge. If there is the circle, then you go, oh, it's a negative edge. One final thing. This is a rare, it was pushed by IEEE in the 90s, and it never really caught on, but it is used in a few areas. They have these arrows. If the arrow is on the bottom but not the top, it's a neg edge. If the arrow is on the top and not the bottom, it's a pos edge. But I hate those. Most people hate them because as you get older, these lovely glasses do not make it easy for me to tell which side that arrow's on, unless it's really big. So if you do the circle, I can easily tell. So we're pretty much going to all do the circle form here because you want me to be able to read and grade things correctly. um, but it's also helpful because you're going to work with an awful lot of people who are going to have that. And sad to say, all of us kind of get eye problems at some point. So whatever you can do to make it easier to read later in your life is a good thing. So this is our D flip flop. Again, that's a neg edge. All right. Let's build some fun. So we've got we've done a D. Let's take a look and consider what if I want some other things? What if I really liked um, that SR? Remember the SR? I could tell it different things. I could tell it hold. I could tell it to, um, you know, take a particular value, go to a one, go to a zero. We didn't like the illegal, but if we were to list kind of everything we liked, um, D flip flop still gives me the ability to, put a one in, make the output a one, make the output a zero. Um, I don't have the ability to hold, other than it's in the clock. So the only other thing, if you think a hold means keep your last value, this one tells you go to one or zero. There's only one other possibility that I might be interested in. If I know my old value was a zero, this stays a zero. If the old value is a one, this stays a one. But the only other thing I might want to do is, what if I want to flip that value? Right? Right? And we sometimes call that flip because we're calling them flip flops. We sometimes call it toggle. So these are really the four functions I might want to do with a piece of memory. Hold the value, write a one, write a zero, toggle what I've got in memory. If I take those, just watch my time. Okay, we still have 10 minutes. I'm going to take those four, and we want to kind of make a design for this. So to go through four values, we're going to need two things. We don't want to use S and R, so we're going to do J and K. My wife is telling me I should switch pens. Is that better? We're in with the light glare. Is that better? Much better. Awesome. Yeah, sorry. Sofa is not the best background. I'm gonna have to find a way to mount this nicely to the wall. Then find some spot I can hook my camera up next to it. Okay. So my JK is going to give me different values. So those are my four possible values of my J and my K. Okay, there's something very strange in the chat window. It's a whole bunch of square boxes. Is that a picture? It's a picture of a thumbs up. In mine, it comes across and really kind of hard to read. Okay. Um. Anyway, to get back to where we are, we've got our J and our Ks, and we're going to want to design an input such that we can um, hold different, or take each of those four possible functions that are on here. So we have to also remember at this point what our values of Q and Q prime are. So should say, we could have our value. So I did JK here. I'm gonna do Q across here. Q could be 0, Q could be 1. It kind of forms some options that that are within our system. So if we've got our JK flip flop and we want to be able to do each of these, we have to decide what JK combos mean. So for ours, usually in the book, for instance, will define it for you with an equation for them, which will tell you that it's J and Q prime and all this. But we're going to try to think of it in a little bit of a simpler kind of a standpoint. We're going to deal with kind of this kind of characteristic area. So we're going to make our 0, 0 our no change situation. So this row is going to be our no change. And for our 0, 1, we're going to call that one our reset or make the output 0. And then 1, 0 is going to be our set or make the output equal to 1. And for the 1, 1, we're going to want to toggle. Okay. So I'm going to kind of do this from a design standpoint to pull you back from where you were before. Now, this is a Carnot map setup, right? If you think about it, I have to kind of renumber them to flip these last two, but I'm setting it up almost like kind of a Carnot map, and we'll turn into a Carnot map in a second here. But I wanted to have these in order first. So maybe you want to think of it as a 2-column. We often call these state tables. But anyway, so these are my inputs. When it's 0, 0, I want no change, which means whatever the Q value is, I want that to stay the Q value. So inside these boxes, I'm going to say what the next value of the Q is. This is what it was before, and it was a 0, it stays a 0. It was a 1, it stays a 1. If it's a reset, the 0, 1 case, it was a 0, stays a 0. It was a 1, it goes to a 0. I'm resetting. And if we're at 1, 0, we're at set, which means if it's 0, it goes to 1. If it's a 1, it stays a 1. And then toggle means whatever it was before, it flips. So if it was a 0, it becomes a 1. And if it was a 1, it becomes a 0. Does that make sense? Yes. Okay. Now, to turn this into a Carnot map, all we have to do is get these in the binary order 0, 0, 0, 1. 1, 1 has to come next and 1, 0. So I just have to flip these two elements. There's only 2 here, so there's no flipping necessary. But I have to change the order of these 2. So this is Q. This is when Q is equal to 1. That's when Q is equal to 0. The top 2 do not change. 0, 1, 0, 0. These 2 flip. So the 1, 1 here goes down. And the 1, 0 comes up. And then that means this one comes to the middle. So this is when K, because that 1 comes up here. I have 1, 1 in the middle, K is 1. And these 2 flipping doesn't change it, so J is down here. Good? Oh, that's the thing, it's an NC, no change. We're not getting glare still, are we? Okay, awesome. Thank y'all. I'm going to switch to another card to do the encirclements because now this is a Carnot map. So I have an encirclement here, and I have an encirclement here. Okay. The first encirclement, it's under J and not Q. Good. Awesome. This encirclement that kind of cuts across, it's not K, but it's in Q. Okay, I'll go with yes. All right. So that means that if we're looking at what do we want the next state to be, the equation for it is J Q prime or J prime Q. That is the piece of data that we have to insert. And if we insert this as our data into a D flip-flop, we will then be able to pick these JK values and it will correctly set the value of the flip-flop to whatever you want. You can either tell it to no change or hold. You can tell it to reset. You can tell it to set. Those two together make your data. Or you can do a toggle. You basically have a lot of different ways to treat and alter the bit. Let me mention, so JK flip-flops are potentially they're really cool or they're really annoying. There's not a lot of middle ground. Let me tilt this for a sec because this is just kind of bright light behind me. So JK flip-flops are awesome or horrible. And here's basically why. If you're doing a small design, and that small design involves some memory things and it's a fairly complicated circuit, and you're trying to implement something really confusing, it turns out when you go to do that design, these JK flip-flops, since you have two ways to do anything, and here's what I mean by two ways to do anything. If you look at this table right here, if Q is equal to 0, I've got two different ways I can get a 0. Right? In that same area. If Q is equal to 1, I've got two ways to get a 1. If Q is equal to 0, I've got two ways to change it to a 1. I can either put the 1 in or I can toggle it. If I'm a 1 and I want to go to a 0, I've got two ways to get there. The second you have options when you're doing a design, options mean don't care states. So it turns out that a JK flip-flop, when you're doing a design, will typically turn half of your states into don't cares. And if you remember, don't cares in Carnot maps are like really easy to deal with. So the super nice thing for JK flip-flops is basically if you ever have to do something that's going to involve doing a Carnot map style synthesis, you're building something, JK flip-flops are absolutely your best friend. They will make your life so easy. Small designs, custom weird funky stuff, JK all the way. If it does not meet either of those conditions, then JK flip-flops stink. They're horrible. Right? They because now you have to deal with all this extra complexity when you could have just sent the data in you want. So D flip-flop is by far the most overall useful, but JK when you need it, small design, custom little thing, doing Carnot maps, JK flip-flops cannot be beat under that highly specialized condition. Okay. So that's a JK flip-flop. Um, and then the other type that we sometimes deal with are T flip-flops. So imagine instead of this, we said, a D flip-flop does reset and set, and a JK does all of them. What if I just want to do toggle and no change? Um, That's what a T flip-flop does. So instead of a D flip-flop for data, data just does the middle, T just does these, and JK does all of them. So you might ask, why would I ever want to do a T where I'm doing a toggle? Okay? Um, and so again, just like the JK, a T is a specialized beast that's either going to be a massive pain to you or it's going to be your best friend. So here's where T flip-flops are really useful. Anytime you're counting, if you're building a counter, your bits flip all the time. So timers, counters, anything of that sort, things where they flip a lot, because that's what it does. So this toggling often means, for instance, this is your count, and this is hold between counting steps. So you can build counters and stuff like that really easily. And it turns out there's just a huge number of things that turn out to be based upon counters. So that's a big, big advantage to have them. So T flip-flops are another special beast for a special use. So that's kind of my overview. Those are the three types of flip-flops we're going to use. Probably 90% of the time you'll do a D flip-flop and just be happy with it. The remaining 10% of the time, you'll either need high versatility for a small circuit you're building, you pull out a JK, or you're building any type of a timing counting circuit, in which case you're going to pull a T flip-flop out. All right. I think that I guess I'm a couple minutes over. So, but given our kind of bad off start and the fact that my videos were killing me earlier this week, hopefully that couple extra minutes is helpful. Do any of you have any questions for me? Nope, nope, nope. So we will meet again. Um, we'll keep meeting basically at our time. Um, Watch the announcement board. If I get a chance to um, add a couple more things as kind of like set up the next class, I will. Roughly speaking, I think by the time you get through JKs and the rest of these, you're partway through section 5.5. So somewhere maybe about, um, I think section wise it's about half, but page count wise it's probably about a third or so of it. So we'll try to pick up with the analysis section, is roughly around 5 and 6. Um, when will we be able to see our midterms? I will try to upload the grades for that this weekend. I was trying hard to get all the videos and everything else set up for things. So, sorry I didn't get a chance to post all that. You should also be hearing from the lab section. So we've talked a lot about what to do with the lab stuff, and we've been able to work out a way that everybody ought to be able to get a ability to run kind of Vivado basically, even if you're on a Mac and things like that. So if you haven't heard about the Digital Logic Lab, please check with things because I know that's something we've also spent a lot of time trying to figure out how to do that. So, all right. Well, if there are Julio, awesome. Um, for the midterm. So I'm let's try to shoot. I think it's your most useful to if it's within a couple weeks after I post them. So let's shoot for 2 weeks, but things are pretty chaotic. So if it gets too bad, we can talk about it. but let's shoot for earlier so we can maximize our available time. I want to make sure we get through as much as we can because um, I, I don't I don't like the fact that all of you are kind of suffering through this. So I wish we had a better way to do it. Okay, we got it. Sounds good. If you ever have any questions, shoot me an email. I check them really frequently. Um, and the discussion boards, if all of you check those, I'll try to check the discussion boards every night. That way, if anybody has a question, but the rest of you can check too. That'll kind of become our like frequently asked questions and stuff like that. Uh, just another way that we can all interact. And the announcements and the discussion boards you can respond to. Um, so hopefully that will give you different ways to stay connected. I know all of you, at least when I was there, I always went through and studied together in groups. So hopefully those discussion boards will kind of work like a little bit of group study that you could talk off with each other. Um, does anybody want me to set up a ability? I think I can set up so that you can chat with each other too through Canvas. Is that anything anybody would like? Yeah, all of you are welcome to make a group me if you want. I'm, the only reason I'm suggesting the other ones is it's just stuff I can theoretically set up inside of Canvas. So yeah, if all of you, um, does anybody, is anybody not connected together? Um, because sometimes there's people who, I've found that there's kind of like little subgroups inside. So I'm totally cool if all of you set up a group me. I just don't want some poor person stuck out like, I don't know who's that, and they end up not on the group me. Um, is anybody willing to set up a group me and kind of function as our admin and yeah, I've got an offer from CJ and Tyler. Um, so if the two of you don't mind, just work together, get a group me going. Um, you know, and I'm happy to make sure that gets properly announced through the group and everything, so everybody can get access to it. Um, I just want all of you to have as many options. I know with my kids that the better connected they are, the happier they are, and right now they're struggling because all their friends are gone. So, well, cool deal. Um, any last questions or thoughts, contributions? The group me is a great one. Thank you both. Um, Will the lab will we go through WebEx as well? That's a good question. Since I'm not actually teaching it, um, what my part in this was, I kind of sat down as the I'm the senior digital person, so I work through kind of helping to figure out how can we do this, um, but I haven't heard their final one. We all have a lab partner number, so we can figure out group me after. Um, Okay, that's cool. If anybody's disconnected for the group me stuff, I'll set up a discussion board for group me, and you can just say, "Hey, add me to the group me," and you can talk in there. So I'll make a discussion board for that. Has anybody heard from the lab people? Yes. So that's um, yeah. So it was my suggestion that we mail boards to all of you, um, because I just think you need the boards. So, you know, everybody's been working really hard on this. So I believe you should be getting the boards. Um, so if you're getting like way too many emails, um, I can took away groups as well. Would it be helpful to everybody if um, we had a kind of independent, technically not part of the class, but maybe I'll even ask him if we can do a um, one of these type of WebEx things for the lab. Would that help? Okay, I will contact them. That'll be an action item for me to try to get a WebEx set up for that. But I'll try to get him not to send those. Is there a Canvas page set up for your lab? Oh yeah, no, it's not. Wouldn't be mandatory. Um, I will talk with them about groups. So technically, I'm the senior person on it, but I I don't want to step in and say no, but I will talk with them strongly about ways we can set up groups. So um, the negative of a big group class, I mean, the closest to that is would be more like having a Q&A WebEx that if you had questions, we can come in and do it, or maybe a discussion board, or I don't care, maybe a lab group me or something. I can talk with them about some of those options. Yeah, I think it is helpful to have a little rundown of how the labs worked before. Um, do you know if there's a plan for you to get videos or any type of way to kind of explain the labs? Okay, well, that was quite a few people saying no. Um, okay, I will work on this. I I will contact them and we'll try to get this fixed up for you. So if you get like buried on these things, you can send me questions and maybe that even will be stuff we can kind of talk over a bit. So um, I will talk with them and we'll find out a way, um, you know, to do some type of an intro thing, maybe even like this, where it's an optional thing to come in and we'll record a video and I'll see if there's a way we can try to organize groups better. All right. Yeah, I'm happy to help. So if you need help on any of these things, let me know. I know it's a tough time. What I really want you to do is just be able to learn the material. Um, if you can, I would at least look it over. The best thing. So the question was, should we start on today's lab yet? Um, you know, like I said, I'll try to contact them as soon as I get off to see what we can do about this. If you at least read it over and kind of when you first look at it, you'll figure out, hey, this makes sense, and hey, this doesn't make sense, or you start to try to piece it out. That first grappling, even if you don't get a lot and it feels like you're not getting a lot, it actually turns out that you're at least starting to process the info. You need a first time through to kind of just start figuring out what pieces are there. It's kind of like trying to solve a jigsaw puzzle. got to kind of toss the puzzle pieces out on a big flat area so you can see what you're working with, so that you can even figure out how to grapple it. And so I would encourage you to just try a bit of it and set it up, and that'll give me a little bit of time to try to get this working, and then I'll see if I can get permission for us to all work, or have kind of like a big thing walking you through this. So, and I'll see if we can get groups going. All right. Any other concerns? You are so welcome. All right, I'm gonna call us quits and stop the recording. You're all very welcome. And